Welcome back to Max with RP. Today we are again going to revise the chapter Relations and Functions. Let us see the definition of what is a relation. Let A and B be two non-empty sets. Then the set of all ordered pairs of the form A comma B, where A comes from capital A and B comes from capital B, is called the Cartesian product of the sets A and B and is denoted as A cross B. So A cross B can be written as set of all A comma B, where A comes from capital A and B comes from capital B. So what will be B cross A? It will contain ordered pairs of the form B comma A, where B comes from A and A comes from B. So if the set A has M elements and the set B has N elements, then A cross B will have Mn elements. See, for example, if A equal to 1, 2, 3 and B is the set which consists of the elements 4, 5, then what will be A cross B? A cross B will be 1, 4, 1, 5, 2, 4, 2, 5, 3, 4, 3, 5. So what is n of A cross B? N of A cross B will be 6 elements, which is 3 into 2. So what will be B cross A? B cross A will be 4, 1, 4, 2, 4, 3. Then 5, 1, 5, 2 and 5, 3. So it consists of the following ordered pairs. What is n of B cross A? N of B cross A is 6. Now, if A and B are finite sets consisting of M and N elements, then what is how many elements does A cross B have? M into N. So it will have M into N ordered pairs. Now what is a relation? Relation is the set of all subsets of A cross B. The set of all ordered pairs of the form A comma B, where A comes from capital A, B comes from capital B, is called the Cartesian product and it is denoted as A cross B. The set of all subsets of A cross B are called as relations. If A and B are finite sets having M and N elements respectively, then how many relations are possible? Mn is the number of elements of the Cartesian product. Therefore, the total number of subsets or the number of relations that are possible is given by 2 power Mn. Now let us look at this problem. P is the set of even numbers less than 10 and B is the set of prime numbers less than 15. You have to find the number of relations from A to B. So A is the set of all even numbers less than 10. So A equal to 0, 2, 4, 6, 8. B is the set of all prime numbers less than 15. So 2, 3, 5, 7, 11 and 13. So how many elements does the Cartesian product A cross B has? This is 5 and this has got 6. So A cross B has 30 elements. So how many relations are possible? The number of relations will be 2 power n of A cross B, which is 2 power 30. So is it clear how to find the number of relations from one set to another? Find the Cartesian product. Look at the number of elements in the Cartesian product. If A as m and B as n, the Cartesian product as m into n, the number of relations is, the total number of relations is the total number of subsets, which is 2 power mn, 2 power, for example, in this case, 5 into 6, 2 power 30. Now we are going to define what is a reflexive relation, what is a symmetric relation, and what is a transitive relation. A relation R from a non-empty set A to itself, we can say A cross A, or we can just say A, R as a relation on a set A. A relation R on a set A is called as a reflexive relation if every element of A is related to itself. That is, if A comma A belongs to A for every A in capital A. First, let us understand the definition, then I will illustrate with the help of an example. A relation R on a set A is said to be symmetric if A is related to B implies B is related to A. That is, if A comma B belongs to R, then B comma A should also belongs to R. A relation R on a set A is said to be transitive if A is related to B and B is related to C implies A is related to C. That is, if A comma B belongs to R and B comma C belongs to R implies A comma C belongs to R for all choices of A, B, C in R, then we say the relation R is transitive. If a relation R is reflexive, symmetric and transitive, it is called as an equivalence relation. Now let us look at the figure. Let us think that set A is the set of all lines in a plane. Set of all straight lines in a plane. Let us suppose the relation R is defined as follows. Two lines are related if they are perpendicular to each other. L1 is related to L2 if L1 is perpendicular to L2. So what is A? A set, we are defining a relation on a set A, where A is the set of all straight lines in a plane. When are two straight lines related? If they are perpendicular to each other. Now we will check whether such a relation is reflexive, symmetric and transitive. If you take any line, is it perpendicular to itself? Can it be perpendicular to itself? It's not possible, right? Therefore, R is not reflexive. So it is not reflexive. Why? No line can be perpendicular to itself. Now, if L1, what about symmetry? If L1 is perpendicular to L2, implies L2 is perpendicular to L1. If one line is perpendicular to another, the other line is perpendicular to the earlier one, the first one. Therefore, this is true for any choice of two straight lines which are perpendicular to each other. You consider two lines L1 and L2. Suppose they are perpendicular, L1 is perpendicular to L2, it means that L2 is also perpendicular to L1. So symmetric property is satisfied. What about transitivity? Let L1 be perpendicular to L2 and L2 be perpendicular to L1. L3. L1 is perpendicular to L2. L2 is perpendicular to L3. Then what will happen? See, L1 is perpendicular to L2. Now L2 is perpendicular to L3. Then what can you say about L1 and L3? They are parallel. L1 will be parallel to L3 and not perpendicular. Therefore, it is not transitive. So this relationship of perpendicularity is not reflexive, it is symmetric but not transitive. If all the three conditions are met, then we say such an equivalence, such a relation is an equivalence relation. See, suppose you consider the set of all straight lines in a plane. So this is example 1. Let us look at example 2. So A is the set of all straight lines in a plane. Relation L1 is related to L2 if L1 is parallel to L2. Instead of perpendicularity, I am defining the property of being parallel as the relationship. Two straight lines are related if they are parallel. So now we will think about all these three: reflexive, symmetry and transitive. Is it reflexive? Every line, is it parallel to itself? Yes, isn't it? It's coincident. Coincident lines are also parallel to themselves. So it is reflexive. What about symmetry? If L1 is parallel to L2, automatically L2 is parallel to L1. Therefore, it is symmetric. If L1 is parallel to L2 and L2 is parallel to L3, then you can say that L1 is parallel to L3. Therefore, it is also transitive. So, the relationship of being parallel is reflexive, symmetric and transitive. So, to summarize, a relationship R, a relation R on a set A is said to be reflexive if A comma A belongs to R. It should be related to itself. Every A should be related to itself. How do you write it in the form of ordered pair? If A comma A belongs to R for all A in A. When do you say it is symmetric? A comma B belongs to R implies B comma A belongs to R for all A comma B belonging to A. What is the meaning of transitivity in terms of ordered pairs? If A comma B belongs to R and B comma C belongs to R, then A comma C belongs to R for all choices of A, B, C coming from capital A. So the same definitions, but we have expressed it in the form of ordered pairs. Now, let us look at an example. So we will look at two numbers. So on a set of R of real numbers, we will define x is related to y if x is less than y. So what is our set of real numbers here, and what is the relationship? Two numbers are related if x is less than y. We say x is related to y if x is less than y. So now you can ask, does it satisfy the conditions for an equivalence relation? So that means x comma x should belong to R. Is x less than x for any x? It is false. 2 less than 2, not true. It is false because 2 is equal to 2. So x is less than x is not a true statement, therefore it is not reflexive. Now, is it symmetric? To disprove a statement, even if you can come up with one counter example, it is sufficient. To prove a statement, you have to give a general proof. So, if 2 is less than 3, we know that, but 3 is not less than 2. So, not symmetric. Is it transitive? So, this is, we checked for reflexivity. Then we checked for symmetric. Next, transitivity. X is less than y and y is less than z. So what does this imply? X is less than z. Is it a true statement? Yes. Logically, it is a true statement. Therefore, it is transitive. So transitive, yes. Reflexive, no. Symmetry, no. So to disprove something, you can give a counter example where the relationship fails. Let S be the set of, this is a multiple choice question. Let S be the set of all real numbers. Then the relation R equal to set of all A comma B such that 1 plus AB greater than 0. Then several combinations are given. Is it reflexive, symmetric, not transitive, reflexive and transitive but not symmetric? 4 options are given. We will analyze the given problem and check which of the options is correct. Okay, now what is the relationship given? Let S be the set of real numbers and R, what is the relationship? R equal to set of all A comma B. That is A is related to B if 1 plus AB is greater than 0. A is related to B if 1 plus AB is greater than 0. First, we have to check for reflexivity. What do you mean by reflexivity? A is related to A for every A. So, choose any A from the set of real numbers. Look at A comma A. Does it belong to R for every choice of A? Now, consider 1 plus A into A, which is 1 plus A square. A square being a square is always positive. So, this is greater than 0. So 1 plus A square is greater than 0 for every choice of A. 1 plus A square is greater than 0 always. So A is related to A for every choice of A. Now what about symmetry? 1 plus, let us suppose A and B are two real numbers such that 1 plus AB is greater than 0. If 1 plus AB is greater than 0, you know that AB is the same as BA. Multiplication is commutative. So 1 plus AB is greater than 0 will imply 1 plus BA is greater than 0 for all choices of A comma B in capital A. Now what about transitivity? Okay. Now to say something is not true, I have told you that you have to come up with a counter example. So you have to play with numbers, check for different choices of ABC, check where it is working and where it is not working. If it is not working for even one choice of ABC, then it is not transitive. So I have chosen A equal to -1, B equal to 0, C equal to 2. Now let us verify whether it is transitive. Now what is 1 plus AB? 1 plus AB equal to 1 plus -1 into 0, which is 1 greater than 0. So A is related to B. What about B and C relationship? 1 plus BC will be 1 plus 0 into 2, which is again 1 greater than 0. So B is related to C. So A is related to B, B is related to C, but what about whether A is related to C? You have to check 1 plus AC, which is 1 plus -1 into 2. 1 minus 2, which is -1, which is less than 0. So A is related to B, and B is related to C, but A is not related to C. Therefore, it is not an equivalence relation. Why? It is true for reflexivity, it is true for symmetric, but it is not true for transitivity. So are you able to follow what we have discussed so far? So I have just given you a few examples of relations which are equivalence relations and some which are not. So please go through this video and remember to subscribe to the same and I hope you found the session useful. So until we meet next time, it's goodbye from Max with RP.